Hey everyone, this is David Brown with video 2 of our Abstract Algebra course. Today I'm going to cover section 1 from this book, Abstract Algebra, a First Course by Dan Saracino. And in the last video, we covered section 0, which was a review of sets and also mathematical induction. Section 1, we're going to talk about binary operations. And the reason that this is important is because in section 2, we're going to define what a group is. And binary operation is part of the definition of group. So today we're going to cover what a binary operation is. Let me first read the definition, which is a little bit confusing. If S is a set, then a binary operation star on S is a function that associates to each ordered pair, little s1, little s2, of elements of S, an element of S, which we denote s1 star s2. Okay, so what does all of that mean? First of all, we have an operation. And you can just think of this for the time being as like addition or multiplication. It's denoted by star, but really that's just a placeholder. It could be any operation or function. And when we're talking a binary operation, we're not just talking about the operation itself, like addition or multiplication, but we're talking about it linked to a specific set. So it's the operation combined with the specific set that gives us a binary operation. Next, we have an ordered pair, S1, S2. So we're taking two elements from the set, and it can be the same element. And what we're doing is we're performing the operation, but it is an ordered pair, so order matters. So S1 star S2 might be different than S2 star S1. And when we perform that operation on those two elements, the result that we get is another element of that same set. Okay, so basically we're taking two things from the set, we're performing this operation, and whatever the result is has to come from the same set. So let's look at a couple of examples. So if we look at addition on the positive integers, we're looking, is this a binary operation? So what we have to think about is if we add two positive integers, is the result always a positive integer? And the answer is yes. Whatever two positive integers we add, we get another positive integer. What about subtraction? If we do subtraction on the positive integers, well, if we do 5 minus 3, that gives us 2. So that holds. But what about the other way? What if we do 3 minus 5? That gives us negative 2, which is not a member of the positive integers. So therefore, addition on the positive integers is a binary operation, but subtraction on the positive integers is not a binary operation. What about subtraction on all of the integers? If we subtract one integer from another, is the result always an integer? The answer is yes. So subtraction on all of the integers is a binary operation. We can also look at multiplication. For example, multiplication of the positive integers. If you multiply one positive integer by another, do you always get a positive integer? And the answer is yes. And it turns out that holds true for the integers, for the real numbers, and for the rational numbers. Now let's look at division. What about division? And let's look at the positive real numbers. If you divide one positive real number by another, does that give you another positive real number? The answer is yes. What if we do division on the integers, though? This is an easy one to prove. What if we do 1 divided by 2? Well, that gives us 1/2. That's not an integer. So division on the integers is not a binary operation. We said that division on the positive real numbers is a binary operation. What about division on all real numbers? And you might go through some examples in your head and say, yeah, when I divide that, it seems to hold true. But there's one problem, and that is the number 0. If we try to divide, 0 is part of the real numbers, but we cannot divide by 0. Division by 0 is undefined. Therefore, division on the real numbers is not a binary operation. It goes on with some more examples. We don't only have to do addition or multiplication, division, these very simple things. We could also define it as a star b equals a cubed plus b squared plus 1. And if we went through that, we would discover that that is a binary operation on the integers, the rational numbers, the real numbers, the positive integers, the positive rational numbers, and the positive real numbers. We could also deal in a different way. Let X be a set. Let S be the set of all the subsets of X. It turns out union and intersection are both binary operations on the set S. Another example, let S be the set of all 2x2 matrices with real entries. The matrix product is a binary operation on X. So you can see we're going beyond just the simple idea of adding or multiplying numbers. These can apply to equations. This can apply to matrices. There's all kinds of different ways we can define it. So when we're talking abstract algebra, we're taking those simple concepts we learned in algebra and making them more abstract. Next, we define commutative and associative. If star is a binary operation on S, then star is commutative if S1 star S2 equals S2 star S1 for every S1 and S2 that belongs to S. So when we're talking something being commutative, it just means, does the order matter? If the order does matter, it's not commutative. If the order doesn't matter, if we can always switch places, do S1, S2, or S2, S1, then it is commutative. Likewise, we have associative, where we're looking at 3. And the idea of associative is basically if we have S1 star S2 star S3, doesn't matter how we group them. In other words, do we get the same result if we do S1 and S2 and take that result and start with S3? Is that the same as if we did S2 star S3 first and then did S1 star that result? So commutative has to do with order, associative has to do with grouping. And these two properties aren't necessarily related. So because a certain binary operation is commutative, that doesn't tell us anything about whether or not it will be associative, and vice versa. So these are things we have to prove independently. And another note that the author makes at the end is when we're doing simple math, sometimes we take for granted ideas such as things being commutative or associative because it applies for things like addition and multiplication. However, when we're dealing with sets in this book, whenever we're defining something new, we can't just assume that it'll be commutative or associative. It's always something that we need to prove for that particular binary operation. And to end the chapter, it gives the definition of symmetric difference. And this is defined as the set of all elements that belong to one set but not to both. And there's two definitions, and both of them make sense. So if we wanted to find out what elements are in one set but not in both, the first thing we could do is we could take one set minus the second one. So that gives us everything that's in one but not the other. And then we do the opposite. We take the other set and subtract out the first one. And whatever is left is what was only in the first one. Then we take those two results and we add them together, we combine them. So that's one way of thinking about it. The other way of thinking about it is to do the union of the two sets. So that'll give us everything. And then we subtract out the intersection of the two sets because the intersection is what is in both sets. So either way you want to look at it, the basic idea is it'll give us everything that's only in one of the two sets but not in both. And I think the reason they give the definition here is only because they want to use some of the concepts we learned to be able to prove it. So I don't know that that's something we need to use right away, but it is included in this section. Okay, that was today's section, a little bit shorter than most sections, but next we'll get into groups and really start into real abstract algebra. If this was helpful, please like and subscribe and come along with me on this journey learning math.